So now we're going to talk about the last two measures of dispersion. First one is the variance, and the second one would be the standard deviation. So the variance is often described as S squared. It's the average of the mean value of the squared deviations of the scores from the mean. And it sounds complicated, but it actually isn't quite that complicated. And once you get the hang of it, you'll be able to do this very easily. Computationally, the equation is actually very similar to the mean deviation. The only difference really is that for the mean deviation, if you remember, we took the sigma, or the sum value, of x minus x bar, but that value was the absolute value. We didn't look at any of the signs. There was only the positive values. In this case, we actually are looking at the true values for the variance. We're looking at the true values, x minus x bar, but we're squaring those true values and then dividing that total by n. So the variance is actually much larger than the mean deviation because we're actually taking the squares of the deviations. So looking at this table, which looks very familiar to you now, it's very familiar. We have x, which is the number of cups of coffee. We have x bar, which again is the mean for x, which is in this case 8. We have x minus x bar, which is simply 12 minus 8, 10 minus 8, 10 minus 8, and so on, all the way down. And that's exactly how it was set up for the mean deviation. So nothing is new in those three columns of data. The only thing new is this last column of data now, where we are introducing x minus x bar, this column of data here, but squaring it. So we're doing 4 squared is 16, 2 squared is 4, 2 squared is 4, 2 squared is 4, negative 3 squared is 9, negative 3 squared is 9. So we're actually, even though we're not looking at the absolute values, we're looking at the true values, we're not ignoring the negative sign. It doesn't matter because if it's a negative number and it's squared, it's going to become a positive number, right? Two negative numbers multiplied to each other is a positive. So negative 2 times negative 2 is 4. Negative 3 times negative 3 is 9. So this column is x minus x bar squared is represented right here by this column. And in order to get the variance, all you're doing is taking the sum of that column and dividing it again by the sample size. So sum of this column is 46 divided by n. That's 46 divided by 6 equals 7.67, which is the variance. And the last measure of dispersion is the standard deviation. The standard deviation, which is symbolized by S, is ultimately essentially just the square root of the variance. So the variance S squared is usually larger than the mean deviation because we actually took the squares of the deviations. But another way of calculating the variability around a mean is to standardize that variance, the standard deviation. So the standard deviation is the same as the variance, except we take the square root of that variance to estimate, to calculate it. So here is how it looks if we actually write it out. It's basically the ultimate goal of the standard deviation is to provide a measure of dispersion that's actually closer in size to the mean deviation than the variance. So computationally, nothing has changed here in the standard deviation for the standard deviation table. This is the same as the variance table. Nothing has changed at all. Again, we have x bar of column, x minus x bar, which is this column minus this column. And we have this x minus x bar squared, which is again this column here squared. And in order to get the variance, we would take the sum of this value here, which is 46, and you would divide that by the sample size, which is 6. So 46 divided by 6. So we know the variance is 46 divided by 6, or the sum of x minus x bar squared divided by 6, or the sample size, which is 7.67. This is all just reiteration of what we just did in the previous slide. So now the standard deviation, which is just simply S, is just taking the square root of this 7.67, and that gives you 2.77. So what we've worked on so far with the measures of dispersion was using raw scores, raw data, without any frequency data. For example, Here, it's raw because we have 1, 2, 3, 4, 5, 6 people represented with 6 rows of data. With frequency data, it's a little bit different. If you remember, we have frequency data where we actually have categories of data represented by the rows of data. So for the variance in the raw scores, this is just recapturing exactly what we have in a previous slide. It's the sigma or sum of x minus x bar squared divided by n. For frequency data, actually, the equation is actually adjusted slightly so that we're actually multiplying each squared deviation by the frequency of that particular value of x. Okay, so it looks busy, it looks more complicated than it is. So here's another table of, this is frequency data. Again, the variance is calculated as the sigma of the x minus x bar squared times the f. Okay, so again, like we did for the mean, with frequency data, we had to multiply items by f. We're going to do the same thing for the frequency data for measures of dispersion. So here we have, this is frequency data, so I have grouped the number of cups of coffee, 12, 11, 10, 9, 8, 7, 6, 5. F stands for frequency, so one person had 12, 0 people had 11, 2 people had 10, 0 people had 9, 8, or 7, 1 person had 6, and 2 people had 5. Okay? So if I take the sum of this column, which is F, the sum of the frequency, I should get the sample size, which is 6. So sum of F equals 6. And then the column here is Fx, which is simply just F times x. It's just 12 times 1 equals 12. So what this gives me is the total number of cups of coffee. So 0 times 11 is 0. 2 times 10 is 20. 0 times 9 is 0. 0 times 8 is 0. 0 times 7 is 0. 1 times 6 gives us 6 cups of coffee. 2 people had 5 cups of coffee, which gives us 10 cups of coffee total. So if we sum f of x, or fx, that gives us 48. So you add all these up and you get 48. So sum of fx is 48. So in order to calculate the mean using frequency data, we would take 48 divided by 6, or the sum of fx divided by the sum of f. And that gives us 8 cups of coffee. So our x bar, or the average number of cups of coffee, is 8. So I'm going to enter that right here, x bar, 8, 8, 8, all the way down. And then very similar to what we do with the raw data, we're going to do x minus x bar. And in order to calculate x minus x bar, all we're doing is literally taking x, which is here, minus x bar. So 12 minus 8 is 4. 11, which is x, minus 8 is 3. 10 minus 8 is 2. 9 minus 8 is 1, all the way down. So we calculated a new x minus x bar for the frequency data. This won't be the same as the raw data because the numbers are representing actually frequencies, not actually individuals. And here we have x minus x bar squared. Again, exactly the same as we did for the raw data. You're going to take this value here, this x minus x bar column, and you're going to square it. So 4 squared is 16, 3 squared is 9, 2 squared is 4, all the way down. Again, squaring a negative value gives us a positive value. So we have all of these squared values here, x minus x bar squared. All of these are just squared values of x minus x bar column. And the last step, which we haven't seen before, is multiplying this column now by the frequency. So again, with frequency data, we always end up multiplying by f. So 16, which is this value here, and this is just simple arithmetic, really. It's x minus x bar squared, 16, times the f. So 16 times 1. 9 times the f, which is 0, 0. 4 times the f, which is 2, 8. 1 times 0 is 0. So again, if you just follow the simple math here, it's this number here, represented right here, times, big X times F, 16 times F, 9 times F. 4 times 1 is 4, and 9 times 2 is 18. And the last step here is to simply take the sum of this value here, this column here, and divide it by the sample size. So that's the sum, it's represented here in this value, in this equation here, sum of the x minus x bar squared times f. So sum of this column, which is 46, dividing it by the sum of f, which is the sample size, 6. So 46 divided by 6 gives us 7.67. And lastly, the standard deviation is only the square root of that the variance, which is 7.67. So the square root of 7.67 is 2.77. And the one thing I wanted to mention, overarching principle with measures of dispersion, is essentially, I want to reiterate this, is all you're basically doing is trying to estimate how much noise there is, how much error, if you will, there is around a mean. So we might be able to see that there are 8 cups of coffee here. There's 8 cups of coffee on average per person, but that 8 cups of coffee could be more. The value for each person could actually be more, or it could be less. And so in order to capture how much more or less across all people in your data set, we need one value, and that one value is your measure of dispersion. And in this case, we're using variance, standard deviation, and mean deviation.